Geosim, photorealistic image simulation with geometry-aware composition for self-driving. In this paper, we tackle the problem of generating synthetic camera data for training and testing the full autonomy system, including perception algorithms. For example, how would the autonomy system perform if a new car was observed here? Past methods for image simulation are either physics-based rendering approaches, which require significant manual effort to achieve photorealism, or data-driven generative models, which lack a connection to the underlying geometry of the scene and have visual artifacts. In this work, we present Geosim, which leverages both methods to achieve scalable, photorealistic, traffic-aware, and geometrically consistent image simulation. We now give an overview of our method and show qualitative results. First, Geosim leverages real-world camera and LiDAR data, along with bounding box annotations, to reconstruct vehicles encountered in the wild. We develop a self-supervised 3D reconstruction network that takes sensor data from multiple viewpoints for a given vehicle and outputs a high-precision 3D shape with image texture. Our large and diverse vehicle bank has over 8,000 unique assets. With this 3D vehicle bank, we can conduct geometry-aware image simulation by inserting a novel object into recorded real-world data. Given an existing scene, we can sample a plausible placement in the traffic, retrieve a textured 3D asset, and then animate the object with kinematics to interact with the existing traffic. Given the placement in selected vehicle, we render the vehicle at a new target pose to generate its target view. We account for occlusion by using a pre-trained depth completion network. Finally, we perform post-completion image synthesis. We apply a neural image synthesis network so that the vehicle fits in seamlessly. Additionally, since our assets are 3D, we can render with ambient lighting and generate soft shadows. Here's an example of our approach applied to video simulation. For each sequence, we first show the Geosim simulation at real-time speed, and then the slowed-down version. Notice that our simulated images are temporally coherent, and that the added vehicles obey traffic and have reasonable motion. The added vehicles are hard to distinguish from the real ones. Additionally, multiple objects can be added to the scene and interact with each other, such as dynamic lane changing and turning. We can simulate consistently across reasonably long time horizons. Also, notice that Geosim's retrieval-based approach from real data allows us to simulate flashing braking lights. Notice that in this scenario, the simulated vehicles are moving at high speed and look reasonable, creating an interesting scenario. Being 3D aware also means we can also do multi-camera simulation that is physically plausible. Here's the top view that shows one of the side cameras, while the bottom view shows the main front-facing camera. The Geosim simulation is consistent for both sensors. Here are some additional qualitative examples. Can you determine which vehicles are simulated? Geosim can generate vehicles at diverse viewpoints, while also handling occlusion from static background and construction, other vehicles, and even pedestrians. Here's another set of examples. It's difficult to tell at first glance which cars are simulated. Geosim simulated images are significantly more realistic than the baselines. While one can easily and quickly detect the added object in other methods, due to unrealistic generation creating smeared cars or geometrically invalid results or unrealistic appearance, one must look closely at Geosim images to distinguish the added object from the real ones. Each component of Geosim plays an important role in photorealistic image simulation. Removing occlusion handling, image synthesis, or ambient occlusion causes obvious artifacts. With Geosim, we can obtain cost-free data annotations for training and testing perception models, such as for semantic segmentation. Our approach is also generalizable to publicly available datasets, such as Argoverse, and we achieve strong visual performance over other baselines. Thank you.